This video examines the index of hydrogen deficiency, its uses, and how we can calculate it from a structure and a formula. The index of hydrogen deficiency is a number of molecules of H2 which would have to be added to the molecule of interest to convert it to a saturated acyclic compound, meaning our molecule of interest would have no pi bonds or rings. If we remember, a saturated formula has the form of CnH2n plus 2. Anything less than this is considered an unsaturated compound. This is also called degrees of unsaturation. When examining what the deficiencies are, one ring equals one deficiency. One double bond equals one deficiency because a double bond, as we remember, contains a pi bond. A triple bond equals two deficiencies because a triple bond contains two pi bonds. When we determine the overall deficiency of a molecule, we add up the rings, double bonds, and triple bonds that are present within that molecule. The index of hydrogen deficiency can be very useful in structural determination. A great deal of information can be obtained about a molecule before a single spectrum is even examined. An important thing to note is that the HDI must be a whole positive number to be a reasonable formula. If you do not have a whole positive number, your formula cannot be considered reasonable. And a good rule of thumb is an HDI of 4 or higher is usually indicative of the presence of an aromatic ring. Now that we know the definition of an HDI, let's look at some examples and start to determine HDIs. So looking at these structures, we can determine the HDI from just the structure shown. Looking at our first structure, we can see we have one pi bond, a second pi bond, and a third pi bond. We also have one ring within the structure. If we add all these up, we get an HDI equal to 4. Now let's look at our second structure. We have a triple bond and a double bond. If we remember, the triple bond contains two HDIs, and a double bond contains one. Adding those up, we get an HDI of 3. Now looking at our third structure, we see we have the presence of an aromatic ring. And we can see in that aromatic ring, we have one double bond, two double bonds, three double bonds, plus the ring itself. That's where the HDI of 4 for an aromatic ring comes from. We also have a triple bond that contains an HDI of 2 and a carbonyl. The carbonyl contains an HDI of 1. It's important to remember it doesn't matter which atoms are connected by the pi bond, just as long as there's the presence of a pi bond. Adding all these three structures up, we get an HDI of 7. We can see on our fourth structure in the bottom here, we have that aromatic ring, and we know that aromatic ring has to have an HDI of 4. We also see we have a nitro group here. If you're unfamiliar with the nitro group, please familiarize yourself with it now. Within the nitro group, it contains one pi bond. So that means this molecule has an overall deficiency of 5. Our final structure we see here is one that has been in the news quite often recently. This is the structure of hydroxychloroquine. We can see, even though it looks complicated, we can still determine the HDI. We can see we have 1, 2, 3, 4, 5 pi bonds, and then 1, 2 rings. And we examine the rest of the molecule, and there are no pi bonds or rings in the rest of it. So that means overall hydroxychloroquine has an HDI of 7. So as you can see, looking at the structure and determining the HDI is a fairly straightforward process. Just add up the rings and the pi bonds that are present. Sometimes we do not have the structure already drawn for us, but we can still determine the HDI. So we can use this useful formula to figure out what the HDI of any molecule is. If we look at our formula, we can see that we have the 2 carbons times 2. That would give us a fully saturated compound, if we remember from earlier. From that formula, we then subtract out the number of hydrogens that are present. Then we subtract the number of halogens. Since halogens form one bond, they act like a hydrogen atom for the purposes of HDI. Then finally, we add in the number of nitrogens. The reason we add the number of nitrogens is nitrogen forms 3 bonds, 1 extra for purposes of HDI. We take this number and we divide it by 2 to figure out what the HDI is. In this formula, oxygen gets ignored since oxygen typically forms 2 bonds. So now let's look at this formula and use it for a few examples to familiarize ourselves with how to figure out the HDI for molecular formula. So looking at our first problem, we have C5H10. Using my formula, I would take 2 times 5, the number of carbons, plus 2. This gives me a fully saturated compound. Then I subtract out the number of hydrogens, and I don't have any halogens or nitrogens. Take all that and divide it by 2. When we plug this into our calculator, we get an HDI of 1. Seems simple and straightforward. This means this formula has to contain either a ring or a pi bond. Looking at my next formula, C3H5ClO. I do the same process, 2 times 3 for my number of carbons, plus 2. Subtract your number of hydrogens, subtract your halogen, and oxygen we ignore. Take all that, divide it by 2, you should end up with an HDI of 1. So again, this means this compound has to contain either 1 ring or 1 pi bond. Looking at our third formula, we can see we have C5H10O2. We can do the same process as we've been doing, but you can see with oxygen, we ignore it, so we don't include it in our formula. So our calculation becomes the same as our first problem here, which means we still have an HDI of 1. So looking at our fourth formula, we can do the same process, where we have 2 times 4 plus 2, subtract out 6 for the hydrogens, and 2 for the halogens since I have 2 bromines. Divide it by 2, and we end up with an HDI of 1. And then looking at our fifth example, we have C5H9NO2Br2. Now this contains all of our possible heteroatoms. It contains a nitrogen, an oxygen, and a halogen. So we still do our calculation the exact same. So we have 2 times 5 for a number of carbons, plus 2. Subtract your number of hydrogens, subtract your number of halogens, and don't forget to add the number of nitrogens. It's a common mistake for students to subtract the number of nitrogens as well. Take all of that and divide it by 2. And you should get an HDI of 1. So all 5 of these contain either 1 ring or 1 pi bond. But you can see their formulas vary greatly from each other. And looking at our last formula, we can see it looks a lot more complicated. It's a much larger formula, but don't get intimidated by looking at formulas like this. Instead, just use the formula we've been working with over all these problems. So you have 2 times 18, our number of carbons, plus 2. Subtract our number of hydrogens, subtract our 1 halogen, the chlorine, and then add in all 3 nitrogens. Take all that and divide it by 2. All you have to do is plug this in your calculator, and you should get an HDI of 5. This means for this formula, most likely there's probably an aromatic ring since we have an HDI of 5. It doesn't matter what molecular formula you start with, as long as you use this handy formula to figure out your HDI, you should get it right each and every time. It's a good idea to memorize this formula. This way you don't have to go look for it every time you want to figure out your HDI. And this concludes our Index of Hydrogen Deficiency lecture. You should be able to now determine the HDI from a structure and also the HDI from a molecular formula.